The topic that we're going to be talking about today is a little bit about quantization and what's referred to as oversampled noise shaping. And in some respects, oversampled noise shaping is one of the most intriguing topics in the course, in that the way it works is actually a little bit of magic. And also, in the process of kind of going through what we go through in the analysis, there are assumptions that we end up making, that we'll all be making together, that are kind of unbelievable, and that you're kind of surprised you can get away with it. And mainly, you get away with some of these assumptions because what you're trying to characterize is often is something to within an order of magnitude. It's that kind of rough back of the envelope sort of calculations often that you do, but quite often you can get away with it and it works. And of course, sometimes when you do that, you can't get away with it. Now, these are, once again, sort of bullet points that I hope that by the time you've been through this topic, all of these bullet points are going to make sense. Obviously, I'm not going to dwell on them at the beginning. I will bring this slide up again at the end of the lecture. But what I want to kind of draw your attention to now is the key assumption that will pervade this whole lecture, which has to do with modeling quantization error. And quantization is what is just naturally done when you're doing analog to digital conversion. The quantization error is going to be modeled as an additive white noise source that's uncorrelated with the unquantized signal. And I'll say a little bit more about that shortly, but one of the things that it means is as we go through the analysis essentially revolves around issues of talking about a random process, x of n, and in particular, the basic underlying assumption that we're going to be making as we go through this is that the random process is white, it's wide-sense stationary, and mainly for convenience, I'm also going to assume that it's zero mean. Taking into account a non-zero mean is straightforward enough to do, but this is the class of signals that we'll be talking about, and we'll also be talking about putting x of n, or putting a random process through an LTI system with some specified frequency response. Now, in terms of background issues, the sense I've gotten in talking to many of you and kind of seeing sort of what's happened on problem sets, et cetera, is that some of you, I suspect, are very familiar with the details of how to talk about random processes and random processes through LTI systems. Some of you never really encountered that kind of background, and I guess the worst case situation is a situation where you kind of picked up that background, and the terminology I often like to use is on the street. And you pick this stuff up on the street, and often you kind of have it right, but often also some of the key points are just a little off base and trip you up. So I do want to say that as the semester goes along, although random processes is not a major topic in the course, I want to feel free to refer to random processes, put them through LTI systems, and your ability to do that undoubtedly is going to be tested at some point on the midterm. Certainly will be on the background exam, quite likely in the midterm, and also quite likely in the final. And so let me begin by just reminding you of what the key points are that, that we'll want to be referring to in the lecture today. And I would say also that a pretty good measure eventually as to whether you've gotten your background together in terms of random processes is whether eventually all of what we go through today and the clicker problems associated with what we go through today make sense to you. So use that as kind of a metric. Okay, so in talking about random processes, a typical thing to talk about is the autocorrelation function. You can talk about the autocorrelation function as a function of just one variable as long as the process is wide-sense stationary. And by definition, that's the expected value of x of n plus m times x of n. And although we won't be referring much to the term ergodicity, there's a relationship if the process has the property of ergodicity that you can calculate the expected value of this by alternatively doing time averages. But as I'm writing this here, I'm talking about expectations down in ensemble, not time averages. And so then the autocorrelation function has a Fourier transform, and that's denoted phi xx of e to the j omega. Sometimes we'll write it this way. And what that's referred to as is the power spectral density. And there are several things that justify that terminology, one of which is that just simply using a Fourier transform property, phi xx of 0, the autocorrelation function at 0 lag, is 1 over 2 pi, the integral from minus pi to pi of the Fourier transform of that function. And so this is just a straightforward result of Fourier transforms. And so, and this, of course, is also the expected value of x squared of n. And that simply follows from this equation. So it says that the average power or the average energy is the autocorrelation function at 0 lag, and it's the total area that's under the power spectral density. These are all things that you really want to kind of understand where they come from, review them if you're either unfamiliar or rusty on it, and all of this is talked about in the 6011 notes. And then in terms of putting the random process through an LTI system, the relationship between the power spectral density at the output of the LTI system and the input is that that's multiplied by the magnitude squared of the frequency response of the filter. And so, in fact, what that says is it says that the expected value, or the power in the output from an LTI system, is going to be the integral, proportional to the integral of phi xx of e to the j omega, magnitude h of e to the j omega magnitude squared d omega. And in fact, it's this equation that really justifies referring to phi xx, referring to this as a power spectral density, because it says that if I put x of n through a filter which is a narrow band filter, or a filter covering any band, it says that the power that comes out of the filter, which is going to be the part of the signal that occupies that band, that power is going to be the integral of this function just over the band of the filter. In other words, if this filter is 1 in a band and 0 outside the band, then this integration is just going to be integrating this in that band. And that's why it's called, often referred to as the power spectral density. So these are kind of the key points about random processes. Let me just put down one more that I'm going to particularly want to refer to later, and that has to do with putting the random process through a decimator. And the question then with that is, what is the relationship between the autocorrelation function of the output and the autocorrelation function of the input? And it's just one or two steps, but I really urge you to do these steps, work it out for yourself, that the autocorrelation function at the output is simply the result of putting the autocorrelation function of the input through a decimator. So, in fact, there's a relationship, and I'm going to want to be referring to this, that if this autocorrelation function converts to this autocorrelation function simply through the decimator. Now, also, while I have a decimator up here, I just want to also sort out some terminology. Because of some of the dialogue I saw on Piazza and the terminology associated with expanders and decimators. So terms that we've used is upsampling, downsampling, expanders, decimators. There's one other term I'm going to point you to. The question was that I saw floating around on Piazza is, does an expander include the low-pass filter, the interpolating low-pass filter? Well, you can choose whatever terminology you want, but the answer in our context is no. So interpolation or upsampling is expansion followed by the low-pass filtering, or the interpolating, going through the interpolating filter. Then, correspondingly, does the decimator include the anti-aliasing filter? The answer is no in our terminology. Downsampling is anti-aliasing followed by decimation. Now, one other piece of terminology is that decimators, and there are historical reasons for this, which I won't go into, but an alternative terminology for the decimator is a compressor. So in the textbook, often you'll see the decimator referred to as a compressor. Those two are interchangeable. Neither one of those is downsampling. Historically, the reason for compressor is because it's sort of like the reverse of expansion, but it's not really the reverse of expansion. Anyway, that's the sort of terminology that, so you'll see decimation and compression used interchangeably.